So, well, everyone, good afternoon again. So, as Henry said, today we're going to cover some techniques of inelastic scattering, basically time of flight, backscattering, and spinnacle. So, for this initial part, I'll be talking about basic concepts and instrumentation of time of flight and backscattering. So what we've seen so far? Well, we know that when a neutron beam interacts with a sample, one of the possible outcomes of it is a process we call as scattering, where neutron propagation is deviated with respect to the original direction. So the scattering can be either elastic or inelastic. And if it is elastic, there is no exchange of energy between neutrons and sample. So in this case, we are talking about diffraction. If it is inelastic, then there is exchange of energy with sample, and we are talking about spectroscopy. And this is what we're going to cover today. So in this kind of experiments, the quantity we measure is a double differential cross-section, indicated here by the equation for a monoatomic system, just to simplify. So here, SQ omega is known as dynamic structural factor, and it holds the properties and the information about the dynamics of the system studied. And we measure this with spectrometers and different techniques. So if we take the neutron as a wave, the energy of the scattered neutrons can be determined by means of Bragg reflection from a crystal analyzer. And this instrument is called a crystal spectrometer. And if the selection of the incident wavelength is done by a crystal monochromator, then we have a triple axis spectrometer, as Florian explained us last week. But if we take the neutron as a particle, we can then determine the time of flight it needs to travel from the sample to the detector, and thus its velocity or kinetic energy after the scattering process. And knowing the incident energy, the energy transfer can be then calculated. And this kind of neutron spectrometer is called time of flight. A special case of triple axis is the high resolution backscattering. And a special case of the time of flight spectrometer is a neutron spinnacle. And of course, there are also combinations between them. So INS techniques, which are fairly complementary, can be used to obtain information of systems on different time scales, energy range. So for example, lattice vibrations have frequencies corresponding to peak second time range. And these excitations can be observed with time of flight or triple axis. And slower processes, like the dynamics of macromolecules in the nanosecond time range, can be observed with the backscattering or spinnacle. And it makes sense because faster phenomena show broad peaks and slower ones show narrow peaks, which means slower phenomena require a better resolution, as Giacomo is going to explain later. So one thing that we have to keep in mind is that in this experiment, the scattered neutrons, they are being counted in the detector. But the neutron optical elements, they are never perfect. So the measure intensity in the detector is not simply proportional to to SQ omega. It is actually proportional to the convolution of SQ omega with the experimental resolution function R. And R depends on the instrument parameters. So the art of any neutron scattering experiment is to adjust the instrument and its resolution function to the problem under investigation. So now going back to the techniques themselves, last week we've learned about triple axis spectrometer, which is the instrument of choice if a certain region in Q omega is of interest, and if you want, for example, to make repetitive measurements with different parameters such as temperature, pressure, dopant concentration. And due to its detector characteristics, triple axis actually is mainly used for single crystals, and it's not the best option when it comes to the analysis of local excitations and liquids, for example. So it would be nice to have a complementary technique to fill these gaps. So we have time of flight. With time of flight, we can analyze large sections of Q omega, making this kind of map. So the instruments have a large detector integration. This way, it works well for analyzing non-crystalline samples. It works well for local excitations and diffuse peaks. And of course, apart from that, triple axis is available only at continuous sources, while time-of-flight spectrometers are available both at both continuous and pulsed sources. So now, with this background, we can talk a bit more about time-of-flight. So as I said, the time-of-flight technique determines the kinetic energy of a traveling neutron by measuring the time it takes to fly between two fixed points whose distance is known. So considering a generic time-of-flight spectrometer, the neutron beam can be monochromatized by a crystal, by time-of-flight with toppers, or it can be simply pulsed from a spallation source. So the scattering neutrons are then collected in an array of detectors surrounding the sample. And for each detector, the neutrons are counted into a histogram as a function of their arrival time. So these intensity time histograms are the raw data that we obtain. And after treatment, you can convert the time-of-flight axis into an energy scale, for example. So time-of-flight spectrometers can be divided into two classes: direct geometry and the ones with indirect geometry. So in a very basic level here, with direct geometry spectrometer, we have a monochromatic incident beam and the final energy defined by time of flight. With indirect spectrometers, we have a non-monochromatized incident beam and a fixed final energy defined by a crystal. So to understand the accessible regions of Q omega spaces through time of flight, we can start by thinking about the scattering triangles, which we also saw last week. So for direct geometry, the incident momentum of the neutron is fixed, and the momentum of the scattering neutron varies as a function of time. So the inverse is true for indirect geometry. And by applying cosine rule to the scattering triangles and converting the momentum to energy, we can obtain this formula here. And we for each for each geometry, for example, for direct geometry, we can eliminate the final energy for direct geometry, obtaining the first formula. And we can eliminate the incident energy for indirect geometry, obtaining this formula here. So if we keep the same scattering angle, changing the values for the energy, we create curves. And if we do that for a lot of angles, we obtain this region. And we can realize then that these spectrometers have inverted ways. And an important feature of the indirect geometry is the access to a wide range of energy transfers for neutron energy loss. So now let's take a look at the flight path versus time here diagram here for direct spectrometers. So the neutrons enters the chopper with a certain slope corresponding to the velocity of the neutrons. And pulses of neutrons then leave this chopper. And by doing this, they reach the sample. So the neutrons scattered from the sample can either gain or lose energy. And in the middle here, we have the elastic line. So depending on the monochromatic technique, the direct instruments here can be classified as hybrid or chopper spectrometer. So in the first case, the monochromator is a crystal and the analyzer works under time of flight. And in the second case, both monochromator and analyzer would apply time of flight. One example of hybrid is Punter, and one example of chopper is IN5. Punter, which works with thermal neutrons, replaced actually IN4, but their science is basically the same. So their science is basically the same. The neutron beam then is partially monochromatized by disk choppers. And I don't know why the video is not working. I can make it work, but well, however, the neutron beam is partially monochromatized by disk choppers, and then this beam goes to a monochromator already in pulses. So this monochromator will select the incident energy through Bragg's law, and the reflected beam goes through a Fermi chopper, which is a rotating collimator that will turn the beam into small bits. And then they will be identified by time of flight at the detectors. So both the neutron energy and the angle through which the neutron are scattered is analyzed. So this way, you can obtain your scattering function. So Punter has a high flux but medium resolution and can be used to study lattice dynamics, vibrational spectroscopy between 2 and 60 milli-electron volts. In this case, it would be very complementary to Lagrange, which we saw last week. And it's also very helpful to study quantum rotations and translations of small molecules in confinements. Well, IN5, by the other hand, works with cold neutrons. So here, the polychromatic beam is turned into a post-monochromatic beam by a set of 6 choppers. And this provides flexibility to choose an incident energy and to optimize energy resolution. So you have choppers to cut the beam and after that to monochromatize the beam according to its opening time. So these monochromatic neutron bursts are scattered by the sample, and the scattered neutrons are collected by, again, a huge detector. So we will obtain a three-dimensional spectrum with positions X and Y and time. Well, this instrument, it works well for quasi-elastic scattering and inelastic scattering with energy transfers in the order of 1.1 to 250 millielectron volts. Well, as I mentioned before, to know the energy resolution of these instruments is actually very important. So it can be obtained by this formula here, where L2 is the distance between the sample and the detector, and delta T is the pulse width at the detector. So to optimize resolution, the distance between the sample and the detector is made as long as possible. The only limit would be, of course, the expense and the availability of space. But if we think about the resolution as a function of their energy transfer, we have another formula here, where TC is the time of flight at the chopper, delta TC is the chopper burst time, and delta TM is the moderator pulse width. So what we learned from this formula is that if you want a better resolution, then a lower energy transfer is required. And thinking about choppers, the energy resolution varies linearly with the speed of the choppers, but with the cube of the wavelength. So now going to indirect geometry spectrometers, they offer, as I said, access to a wide range of neutron energy loss. And here we use crystal analysis to determine the beam wavelength. And the final energy is fixed. The incident energy is calculated by time of flight between the source and the detection of the neutron after being analyzed. So one example of this kind of spectrometer is IRIS at ISIS, which we're going to discuss a bit later when we talk about backscattering. So in general, indirect spectrometers, they have a better resolution than direct ones. And when we think about energy resolution for indirect geometry, we must know it contains terms related to the uncertainty in the angular spread of neutrons scattered from the analyzer, delta theta A, and timing errors over the incident flight path, increasing L1, for example, which is the distance between the source and the sample, increasing L1 would improve resolution. But here again, there is physical and instrumental limitations. Another possibility for this would be increasing theta A. So now, I just want to show you very quickly some data obtained with time of flight. So for this study here, the aim was understanding the vibration and the lattice excitations of fullerenes at the low frequency range. So here is an example of the structure factor obtained for fullerene. And as I said, time of flight allows us to obtain this map of Q omega, which is very helpful if you don't know exactly what you're looking for yet. And this information can be then rationalized with theoretical calculations. Okay, so Now, let's go back one slide. I said that analyzing this formula by reducing the term related to Bragg's contribution, we would improve the energy resolution. So that's exactly the principle that we're going to see now with backscattering. So the purpose of backscattering is to achieve higher energy resolution. And for this, backscattering uses Bragg reflection at nearly or exactly vertical incidence on single crystals to achieve the highest possible definition of the neutron energy, as it can be seen here for the first derivative of the Bragg's law here. So this highest energy resolution is obtained for an angle of 90 degrees. And in this case here of this instrument, the final energy is fixed. So if we take a generic backscattering spectrometer, if the final energy of the scattering neutron is the same of the fixed for the analyzer, the neutron is reflected by the analyzer and goes through the sample a second time, and then it reaches the detector, which are behind the sample. So in this case, analyzed and non-analyzed neutrons are distinguished by their time of flight. So to better understand how backscattering instrument works, we split them into a primary and a secondary spectrometer. So the primary spectrometer, it defines the incoming neutron beam before the sample. And the secondary spectrometer analyzes the energy transfer after the scattering process on the sample. So the precision at which the neutron energy can be obtained either in the primary or in the secondary spectrometer is given by this formula here. And the first two terms under the root comes from the crystal optics and can be derived from Bragg's equation. And the other term presents the neutron time of flight contribution to the energy resolution. So the total energy resolution of the instrument is actually given by the convolution of the resolution values in the primary and secondary spectrometer. In backscattering, we can have two types of instruments with many differences between them. So in backscattering spectrometer, both primary and secondary spectrometers are crystals. And we have the indirect time of flight, with the primary spectrometer being a time of flight and the secondary a crystal. So an example for the first one is IN13, and an example for the second one is Iris, as I mentioned before. So IN13 basically uses thermal neutrons. And how does it work? Well, I actually had a video here, but it's not working either. So, well, how does that work? So basically, the incident beam is monochromatized by a crystal at almost 90 degrees. It has to have a very small deviation of 1.5 angstroms here in order to keep the beam out of the neutron guide. So this monochromator, it can be heated or cooled to vary the values of the incident energy, since the monochromator itself, it can change its position. So we change the lattice constant D of the crystal. And this beam then is reflected by this deflector here and go straight to a chopper. Sorry. Which cuts the beam for time of flight. And then this beam reaches the sample. So only neutrons with a wavelength of 2.23 angstroms, they are backscattered by the analyzer crystals. And so these neutrons will pass the sample a second time, and then they are registered in the detectors. So IN13 is mainly used in biology since its resolution Q and the energy range is very suitable for dynamic phenomena common to proteins or macromolecules in general. Okay. And here we have IRIS. So IRIS is called a near backscattering instrument, basically because the scattering angle of the analyzer is not exactly 90 degrees. It is 85 degrees, and which means that the resolution of IN13 is better. If I'm not wrong, the resolution of IRIS is around 17 microelectron volts, and for IN13 is about 8. So another difference between IRIS and IN13 is that the analyzed neutrons in IRIS goes directly to the detector without passing through the sample a second time. So now, just to have an idea about which kind of results we can obtain with backscattering, and also to make an introduction about one of Giacomo's topics, which is quasi-elastic. So let's just take a look at this example here. So from quasi-elastic spectra, the information about specific types of dynamics can be extracted. So in this example, quasi-elastic spectra were collected on 3 instruments with different energy resolutions here at ILL. So the spectra measured at different energy resolutions, which varied from 70 microelectron volts to 0.9, enable the investigation of proton dynamics on time scales from 10 picoseconds to 1 nanoseconds. And with this time scale, a wide range of different atomic fluctuations in a protein happens. So from the pictures, we realize that depending on the resolution of the instruments, and specific phenomena actually can be better or worse seen or completely not seen, just proving how important this parameter is, along with the time, energy, and momentum range. So finally, just to sum up the meaning of what we've discussed here, here are some messages. So time of flight and triple axis spectroscopy, they are complementary techniques and have a typical energy resolution of a few % of the incident neutron energy. And in order to improve the energy resolution, we could just narrow the energy band of incident energy, but it would cause a decrease of the signal in the detector. So there are alternative approaches to increase this energy resolution, which are the techniques backscattering and neutron spin echo, which Giacomo is going to talk about after. So thank you very much. Special thanks to the experts, Francesca, Thilo, Jacques, and Marcus. And many thanks also to Giacomo and Mohammed, who helped me out with this presentation.